Hello everyone! Today I'm going to show you two very interesting derivations about two very fundamental equations to do with electromagnetic waves. The equations I'm going to be deriving are as follows. E is equal to CB and B is equal to C µ0ε0cE. Now, before we start, we need to make two core assumptions that we know about electromagnetic waves so that the math makes sense. Right. First, we need to assume that the electromagnetic wave propagates in a given direction at a given speed, which means it has velocity, so it's actually moving, which is very important. And number two is that the waves will behave in a sinusoidal pattern, which means they can be described with a sine wave or a cosine wave if you like. So, the direction of an electromagnetic wave is described by the pointing vector, which is the pointing vector, written with a y. It's nice that it has a related name, and mathematically it is P is equal to the E field crossed with the B field over µ0, the magnetic constant. Now, sometimes you'll see this as E cross H, but we're not going to use that right now. All we need to know is the direction of the wave. Now, we're going to start with this and then move on to this. The derivations are very similar. The only difference is we're going to be using Faraday's law for this one and Ampere's law for this one. And it looks similar to that already, so it's fine. Right, so we're going to start by drawing an XYZ plane. Here, with an X and a Z, and start by writing out a differential part of an electromagnetic wave, like this. First, E field, and then the related B field. And then, after a distance of dx, the amount the E and B fields have increased by, which will be E plus dE and B plus dB, right? After a distance of dx, the field will increase by the amount the field increases by. dE over dx is the slope of the essentially the wave, right? Now let's just write down Faraday's law. The closed loop integral of E dot dl, so the produced EMF, is equal to the negative change in time of the magnetic flux. As in, the changing magnetic flux creates an opposing EMF around the loop. Now, what kind of loop do we choose? Vector marks? Well, interestingly, you can do it like this. You write the loop around these E vectors like such that this height is dy. Now, the next thing is we pick a direction for the dl loop. And it's arbitrary, but you have to pay attention to it or you're going to run into unfortunate negative signs that will ruin your work. And I have done that many times and it gets really frustrating looking for them. We're going to pick clockwise, just why not? I guess. So, let's first do the left side. Well, this dy dotted with this E gives us E dy. Now, this dx dotted with an E element is going to be perpendicular, so the dot product will be 0. So none of these sideways elements actually count at all. So next, this E plus dE is actually opposite to the dy, which means we get a negative element. So negative dE dy minus E dy, wrote them in the wrong order, but it doesn't really matter, is equal to the negative change in magnetic flux. Right, we're getting somewhere. Now these two elements here cancel out, and you're left with, well, you can cancel out the negative sign as well, and you are left with dE dy is equal to, well, let's see, the magnetic flux. Well, here is, we need to define what dA is. And what's interesting is you have to define it by the direction of the DL loop here. And the way you do that is you pick a side of the loop here and you cross it with the next side in the direction of the loop. So if you pick this dx, you have to cross it with this dy. And if you pick this dy, you have to cross it with this dx and so on. So by picking this dy and crossing it with the next dx, the final vector of the dA, the orthogonal element of the plane here, is in the negative z direction, which means we actually get the negative sign back. So the equation becomes dE dy is equal to d dt b dx dy. This is the area of the dA element, and, well, that just remains. Now, we can cancel out the dy's, and we are left with dE is equal to negative dB dt, and we're going to move the dx underneath the dE so we can do some nice derivatives with the wave functions. Now I'm going to show those. Those are pretty interesting. You don't need to know these particularly. You could even reason through them with just some basic logic. Let's see. The E wave can be described like this. It is the amplitude of the wave times a sine wave, which then gives you 2 pi whenever time is equal to the period, minus 2 reaches 2 pi whenever x is equal to the wavelength, plus an arbitrary phase shift. Right. Now B is described exactly the same way, just with a b naught. So we're going to write that out. 2 pi over t times t minus 2 pi over lambda x plus phi. Right. Now, as you can see, these are derivatives with respect to x and t. And we're going to just, let's see. The derivative of E with respect to x is E naught times the cosine of all of this times the x elements factor, which is negative 2 pi over lambda. So we're going to write that out. E naught negative 2 pi over lambda times the cosine of, and the insides don't actually matter anymore because, as you can see, both the derivatives will have the cosine of this, so it will cancel out. We're going to write cosine of stuff is equal to the negative derivative of this, which is b naught 2 pi of t, 2 pi over the period of the function, times the cosine of stuff. And as you can see, the 2 pi's cancel out, the cosines of stuff cancels out, the negatives cancel out, and you're left with E naught is equal to b naught, and add the t there and the lambda there. And now with the definition of a few things like lambda f is v, you know this one from simple harmonic motion, you can say that E times f over v is equal to bf, since the period is just the inverse of frequency. Cancel out the f's, and you are left with E is equal to vb, which, well, v is going to be the speed of light, leads to E is equal to c times b. And now, you may have noticed that I dropped the naughts from the E and b, which are the amplitudes of the functions. The reason I can do that is because the waves are always in phase, so they are always proportional to each other no matter what, just by the factor of this c here. And that's the secret to deriving this formula in a way that doesn't involve curl and divergence and complicated mathematics. Now, let's move on to Ampere's equation, Ampere's law. It'll be the same derivation, so we're going to skip a few steps. I'm just going to show you the fundamentals of the equation there. Well, I'm going to show the whole thing, but, we're going to skip the trigonometric part mostly. It's exactly the same. Okay, z, x, y. Now, personally, what I like about these derivations is also that if you really thought hard, you might think of them yourself. It's not the most complicated derivation. It's very satisfying when you do actually go, wow, that actually worked? Damn. But yeah, let's see. Let's draw the same thing again, which is that we have the E field vector, the E plus dE vector, and the associated B field vectors right there, B plus dB. And here, okay, let's just draw out the dx as well. Here, instead of using the loop around the E field, we're going to use it around the B field. Remember what Ampere's law is? With the Maxwell addition, he added the final term to do with the change in electric flux. It goes like this. The closed loop integral of B dot dl is equal to µ0 times the current penetrating the surface we're doing plus µ0ε0, the change in time of the electric flux. Now, this is obviously zero because there are no currents, so that eases our question a little bit. So let's draw that little circle, rectangle out, and it's going to go like this. And this element here is dz. Now, let's see. It's the same method, really, so we're ending up, let's go clockwise again. Why not? Is we get b dz plus db dz, then nothing, and negative, because they're in opposite directions, we get minus b dz, and these two cancel out again, is equal to µ0ε0, and let's see what the change in electric flux is. Now, electric flux can again be described in the same way as the magnetic flux in the previous one, so let's cross these elements in the same direction of the travel. So this dx crossed with this dz gives us, negative y direction, which gives us a negative sign there, a d dt e dx dz. Now the vectors of these things don't really matter anymore because we're only dealing with, we're not actually going to use the vector quantities after this point since everything's dotted. They're scalar products. Right. So we can cancel out the dz here, and we're left with a very similar equation as last time. dB is equal to, excuse me, the negative µ0ε0 dE dt dx. Now we move this dx to this side again, and we're left with a very similar situation as last time. Now I'm just going to write one equation for the waves, and I'm going to say wave is equal to the amplitude of the wave times the sine of the 2 pi over the period minus 2 pi over the lambda times x, oops, forgot a t there, plus a phase shift. Now, let's see, how will the derivatives go? For this side, it'll be b0 times, with respect to x this time, a negative 2 pi over lambda is equal to, we're canceling the trig functions preemptively, don't worry about it, is equal to the negative µ0ε0 and the derivative of this, which will give us E0 with a factor of 2 pi over the period. Now we're going to cancel out a bunch of stuff, the minus signs, the 2 pi's, and that's pretty much it. B0 is equal to the µ0ε0 E0 over the period, and over the lambda, this one, And we're going to rewrite this with this equation in hand again, which is lambda f is v. So this becomes bf is equal to, bf over v. Yes, of course, is equal to µ0ε0 E0 f. And these cancel out and the v travels to the other side, and we are left with b is µ0ε0 v e. And this v becomes b µ0ε0 c e. And this is the final equation. Now, with these two equations in mind, we can actually derive the definition for the speed of light. Now, I will admit this is probably not how it was originally done. Maxwell most likely didn't have these equations in these forms when he did it, but hey, this is how we're going to do it, and it's an interesting derivation anyway. So with the equations in hand, E is CB and B is c µ0ε0 e. We can insert this one into this, which gives us b is equal to c µ0ε0 cb. Cancel out the b's. Gives us 1 is equal to c squared µ0ε0, and that gives us that c is equal to 1 over the square root of µ0ε0. And this is the definition of the speed of light. Now, as you may know, µ0 is defined as the by the force between two 1 ampere carrying cables, 1 meter apart in a vacuum, infinite cables and all that stuff. It's pretty interesting to derive as well, and it's one of the easiest constants to derive because it's defined after it. You can use Biot-Savart's law or whatever. And that's pretty much all I have to say. I hope you've enjoyed, and I hope I've been enlightening in some ways. If you have any questions, please do leave some comments. I would very much appreciate feedback, as this is the first video. Well, see you in the future. Thank you very much for watching. See ya.